Okay, so the exponent on here is going to be positive, right? Okay, we don't want to write all these zeros. Okay, now in order to make that happen, if you look at this first example here, those decimals, that decimal place has to move to the left, right, in order to eliminate them, right? And that's going to mean more in a second. Like, I'm just giving you some general rules. Once you see me actually do the question below, it'll make sense, okay? These are just kind of large number. If I'm converting a large number, here's the generalizations that are going to happen, right? And then if I'm converting a number between 0 and 1, so something small, right, between 0 and 1, the exponent number will be negative. Okay, and the decimal will move to the right. Okay, and we're going to see two examples here where this is the case. Okay. So for those of you, I don't know if you guys have seen scientific notation. I don't really, I don't really touch it in any of the math. Really, maybe it comes up a couple times, but there's no formality of it being in the curriculum from the standpoint. So I don't know if you guys have ever seen this. If you've taken chemistry, probably, right? But scientific notation is always something. It's something to the power of something, right? So it's always like a number times 10 to the power of something, whatever that something is. It might be 7, 5, 4, right? And this dictates how many times you're going to move the decimal place, either to the left or the right. Okay. And so when I'm looking through this, if I'm going to convert this large number to something that looks more manageable, you're only allowed to have, so you can see up here too, there can only be one single digit in front of the decimal. Okay, that's kind of another formality of scientific notation, right? So that means that I have to put the decimal here and here. Okay, well, how do we make that happen is the question, right? So you're saying, all right, well, let's take where the decimal currently is. Okay, we're in a large number situation here, and I need to move it to the left, right? Obviously, because I need it to be right there. How many times, right, is the question. You know your number in scientific notation is going to be something like this. 4.56 times 10 to the something is what we're trying to answer, right? So this something, right, is how many times you need to move the decimal place. Okay, and so when I look at this question, well, here's my decimal currently. Where does it need to go? It needs to go 1, 2, 3, 4, 5, 6, 7, 8, 9 to the left. Okay, now some of you say, well, you moved it 9 to the left. Why wouldn't you make it negative? A negative exponent creates a small number. That's a very small number times 10 to the negative 9, right? But you got to think, what is this number? Like, how do I get this out? If I were to type this into my calculator, I want to get this number back, right? And so if it was negative, I wouldn't get this number back. I would get something very, very small. Right? So you just got to keep that in mind. It's kind of almost opposite, right? Because now you're going to say, this actually means, okay, 4.56, and I'm going to move the decimal place to the right 9 times. 1, 2, 3, 4, 5, all the way over to 9, right? And that's keeping track. Every one of these little bumps is a 0. And that's how you get this back. Okay, that's how scientific notation works. It allows us to take numbers that are going to be a real pain to work with from the standpoint of just how they're how big or how small they are, which is going to come up numerous times in this course. It allows us to work with it because this is much easier to type into your calculator than this, and more consistent. Okay, it's very easy to forget a 0 typing something into the calculator, and you're going to get a wrong answer, right? For no reason. So it's just kind of a necessary skill to make your life easier. Okay, if I look at something like a small number, I'm going to follow these rules here. Okay, we're going to say, okay, well, here's my decimal. How many times do I need to move it? you know your number in scientific notation is going to go 5.43 times 10 to the something. Let's figure out what that something is. We need to go 1, 2, 3, 4, 5, 6, 7. Okay, but we're dealing with a very small number here, so that must mean it has to be negative, times 10 to the negative 7. You're always got to think, well, okay, is my answer is there a connection between my answer and the original question? That's a very common, you see that in math when you check your answers, right? You're always checking to see, okay, is my answer, can I get from my answer back to my question? Okay. If you left it as positive 7, there'd be no way, you'd be going the wrong direction. You'd get a very big number instead. Okay. Do you have any questions of that? You can drop them in the chat. You guys feel free to use the chat. I'm like constantly looking in the bottom right corner of my screen here. Okay. So if you guys have any questions, you can just drop them there. Okay. Now I'll do one of these questions for you just to say, because I didn't really do one up here. But what if I'm giving I talked about it, but I didn't really do one. I'm given scientific notation like this question here. Okay, this is going to be your homework for this chunk of the lesson, okay, just to fill out this table. What if I'm giving something in scientific notation? Well, this thing here, it's telling me to move the decimal place 6 times to the right because the right is positive. Whereas something like this would be 5 times to the left. Okay. And so we're going to go, okay, we're going to take our number there. And we're going to say, okay, I got to count 6 times to the right. 1, 2, 3, 4, 5, 6. Every bump is going to have a 0. So there's your number. 4, 6, 6, 8, 1, 2, 3. Okay. I didn't put any units on here. That's maybe my bad. We could put meters. Okay. You guys can make up your own units for these ones. Okay, that's my bad. Is everybody okay? Let's just go in the opposite direction. Okay, so you guys fill out the rest of those. Okay. Now, this is where I was talking. Things can get a little bit confusing, okay? Good. I also appreciate if you guys drop in the chat. I can't see your faces, right? So I can't tell if A, you're even at the computer, but B, like I can't read the classroom in a normal fashion, right? And so I can't read the body language. So I don't mind. I appreciate if you guys drop it in the chat too, that things make sense, okay? If you guys are feeling okay, if something doesn't feel right, just let me know, okay? So yesterday, I think maybe we talked, like we saw how some of these equations came to be yesterday. Some of these equations came to be, but we didn't really necessarily see on a graph how these things came to be, right? And so that's what we're going to do here. Okay. These are the graphs for 4 different vehicles. Okay, car A, car B, car C, and car D. Okay. And what this is going to ask us is to kind of like use the graph to kind of extract what's actually going on, right? So for instance, like the first part here is which direction is each car traveling? Okay, and what we got to think is like, okay, well, you know, it appears like in the positive direction here, that's implying north, right? And so it looks like all of these vehicles, with the exception of one, are all kind of traveling in the north direction, right? So you can see car A kind of looks like it's traveling in the north direction. Car B, also north. And car C would be north. But then you have this kind of outlier that's going against the overall trends there, right? And you're saying, okay, well, it looks like car D is traveling in the south direction, right? So it's negative. It's slope almost, right? Okay. And then yesterday we talked about what's great about the graphs from the standpoint is like it gives you another layer or lens to look at where those equations kind of came from. And we talked yesterday with the dimensional analysis as to like where did the equations come from? Like how, like you guys remember, I'm sure you all saw this at some point. Or we got the DVT triangle, and we always like, oh, memorize it, right? Well, you don't need to memorize it. Well, sorry, I got it the wrong way. And I know it's the wrong way because I know dimensional analysis, right? We saw if we covered up the V would have been equal to D divided by T. Or from yesterday's lesson when we talked about the dimensional analysis and looking at the units, we know that a distance could be measured in meters and the time could be in seconds. Right? That's where this triangle came from. Right? So there's no need to memorize a triangle. It's understanding what the units are trying to tell you. Okay. Now, if we go one step further, we also talked about like that's kind of a rate of change, right? Like we're traveling some distance for some amount of time. That's a rate of change, right? Rate of change. Can anybody drop in the chat while I'm writing this down what another word for rate of change is? That's okay if you guys don't know. I'm talking from a math lens now. You guys have seen this passage of words before. Rate of change. It's okay if you guys don't know. It's okay. That's exactly why I'm doing this, right? Taking the time to kind of like build you guys up. Rate of change. Well, you guys see you see a very something that should look very familiar to you, right? You guys have seen this for years now. Almost, Jagger. Almost, not quite. Almost. The rate of change is from like a math perspective. We also called slope. Okay, slope was defined as the change in the y's divided by the change in the x's. Or, as you guys knew it, rise over run. Okay, when I talk about, or when we're talking about this graph in particular, like a position versus time, if you guys found the slope of, let's say, car A here, if you found the slope of this line, that's taking the difference between two particular y values and dividing it by the difference between two particular x values, or in this case, position over time, d over t. What does that spit out? Velocity, which we saw yesterday. So a generalization here, right, for these kind of graphs, if we see the slope of a position time graph is going to represent the velocity or speed, okay, depending if you've decided to include what we learned yesterday, direction, okay. If you guys include the direction, it's velocity, okay. So it's down here, it's asking for the velocity, okay, so we're going to include our directions. And so let's say I'm doing car A here, right? And just to save some time, I'm not going to do it 4 times, but I'll do it twice, for instance, okay? If I were to look at, I'm just going to try and find 2 points on this graph that kind of go through a nice grid line. So for instance, I'm kind of seeing 2, one there and one there, right? It doesn't matter what 2 points you pick. The slope is the slope. It doesn't matter if I pick a point way down here and measure the rise over the run. You're going to get the same answer. Okay? I'm just trying to find, I don't know, two numbers that I think might be easy to work with, right? And so you're looking at what's the rise and what's the run. Well, let's take a look at what these 2 y values actually are. Well, the second one, we'll call this D2. And we'll call this D1, right? It looks like I'm seeing 85 as a value over 70, right? And so you're going to go, okay, well, the slope tells me I'm going to go y2 minus y1 divided by x2 minus x1, right? You guys are going to see, okay, what's y2? 85. minus, what's y1? 70. And that's going to be divided by, well, what's on the x-axis? Well, all the time values. Well, what are the time values on the x-axis? Well, let's read down. This looks like t1, and this would be t2. Right, so you're going to go t2. If I changed the variable here so it made more sense, you'd go t2 minus t1. And on the y-axis, you guys would have seen d2 minus d1. Okay, is everybody following? And you can see here, this is the units, meters per second. Like, you're going to get what you're looking for. Velocity, or speed. Okay, so we're going to go 85 minus 70, and we're going to divide that by, it looks like 5.5 and 4.5. Well, that's 15 over 1. And so we're going to get 15 meters per second for car A. And we should say in the north direction. That's for car A. Okay, so we just go down here and we say, okay. Actually, you know what? You know what, Jagger? It doesn't actually matter. And we've seen this in the past. The only thing that matters is that you are consistent. Okay, so if you decided, Jagger's question is, how do I decide which one's which? What you'll see, and maybe this is worth doing, which is fine. This is a review, just to prove to you guys. What if I decided to change this one to D2 and D1? And I change, now, you can't just decide, see Jagger, you can't just decide, oh, I'm going to change it to D1, but I'm not going to change T2. That has to also be T1. Okay, and then this has to be, therefore, T2. Okay, and what you'll see is the math is going to work out the exact same way. The only thing you're going to see here is you're going to go 70 minus 85 divided by 4.5 minus 5.5. So all you're going to see here, Jagger, is that you're going to get negative answers, right? You're going to get negative 15 over negative 1. Well, the negatives cancel when you divide them out, right? And so you're going to get 15 meters per second anyway. Does that answer the question? It doesn't matter, but you have to keep it consistent. You can't just decide to flip things around, like you can't order these differently. Okay? So you have some play there. Okay, now, I think we've done a lot of talking, more than I would have liked to on slope, but that's okay. Okay, I think I might do, I'm just going to give you the answers. We're going to do the exact same work for the other two cars here. So we want to calculate the velocity for car A. We just did. It's 15 meters per second north. You're going to do car B and car C the exact same way. You can find the 2 points on the grid. It doesn't matter which ones you pick, right? I'll start eliminating some stuff here so you guys can see, clean it up, right? So you're just going to find 2 points that the graph goes through nicely, like maybe there, and you can find the slope. And what you'll find is for car B, you're going to see it should be 4 meters per second in the north direction. Car C, you do the same thing. You'll see you'll get 8 meters per second. Now, we've already seen, we know, because we decided, car D is traveling in the south direction, or the negative, right? So we better see either one of two things, right? When we do this work, we're going to see that our slope for car D should be negative, right? So for instance, I'm going to pick maybe that point and that point for car D here. I'll pick different colors so you guys can see it. Okay, car car D, you can see that the slope of this line has to be negative. Okay, well, what is the slope? Well, we're going to go y2 here is going to be, remember, I'm going to define this as 0.2, and then this is going to be 0.1. Okay, and so I'm going to get y2 minus y1 over x2 minus x1. That's going to be 40 minus 80. Right, you can see that there's the y value for this one, 40. And there's the y value for that one, 80. And I'm going to divide that by 5 take away 0. And what are you going to get? You're going to get negative 40 divided by 5, which is going to equal to negative 8 meters per second. What does this negative imply? It implies that it's traveling in the south direction, or its slope is negative, right? So your answer can be one of two things. The negative 8 meters per second, or you can write 8 meters per second south. These are both the same thing. And you can see here, this would be positive, positive, positive. Okay, we talked about that yesterday. Okay. You see okay? Yeah. Is everybody okay? Any questions? What I like about this sheet is it's kind of it's taking some of the stuff that we looked at yesterday, providing some context, and then we're just adding some more layers, right? Which is kind of cool, right? So let's scroll down here. We're going to look at what we can do. Number 4 very quickly, right? We can see which car is traveling the fastest and which one's traveling the slowest. Okay. We can see that car A is traveling the fastest, and the slowest one, well, that looks like car B. Okay, don't be fooled by the fact that just because this is negative, don't just, oh, it's negative, so it must be traveling the slowest. No, it's traveling the exact same speed as car C. It's just going in the opposite direction. Okay, so we're almost looking at the magnitude of the velocity, right? So as to fastest, we're looking at the magnitude of the velocity. That's going to tell us which one is the fastest versus the slowest instead of the direction. Okay, don't let that fool you. Okay. Any questions? I'm gonna do one more thing here. I'm gonna show you guys it's a little conversion, and I included a video in Minds Online to help you with this as well. I'm gonna show you one of them, and then hopefully that makes sense. So if we want to, like, there's lots of instances where, like, I can't contextualize how fast 15 meters per second is, right? Because we don't deal with meters per second in our real life, right? Like a lot of us are just used to, right? And the same thing with the States, right? Like miles per hour. Like I don't know what 50 kilometers per hour necessarily looks like visually in the States in a miles per hour situation, right? So we have these unit conversions, right? And so we're in this position where I don't know what 15 meters per second necessarily looks like. Is that very fast, right? I don't have a reference for that. Okay, it seems pretty fast. Like if you pictured a meter stick and you saw 15 of those every second, that seems pretty quick, right? But relative to our everyday life, like I may want to see what something is in kilometers per hour, because that's what we deal with on a daily basis, right? We're used to driving around in cars that are in kilometers per hour. So let's switch this to kilometers per hour. Okay, well, I'm gonna take an attack angle from like a dimensional analysis kind of perspective, where like I have one unit and I want to get to another, right? And so we're like, okay, well, how would I almost manipulate what's going on here? Well, if I were to rewrite this 15 meters per second, if I were to multiply this by, well, 60 seconds are in 1 hour. Like I've done this strategically because I can see that the seconds are going to cancel now. Okay. But I still have this meter, which is kind of a pain, right? And so I could multiply or try to deal with this meter. Well, how's this going to work, right? Well, 1 kilometer has 1,000. Oh, I forgot one thing, sorry. One step ahead of myself. We also need 60 minutes. Sorry. I made this exact same mistake this morning. This does not make any sense. Hopefully somebody caught that. 60 seconds is not 1 hour. 60 seconds creates 1 minute. I made the same mistake this morning. Right? And this is like, the units are allowing me to see this, right? And you're like, okay, well, I need hours, but I'm stuck in minutes at the moment. All right, so 60 minutes in 1 hour. Now look. Minutes cancel with minutes, seconds cancel with seconds. Okay, so here's where we're at. I basically take 15 times 60 times 60, okay? Or 15 times 3,600, because 60 times 60 is going to be 36 with 2 zeros on it. Okay, and then that has to still, it's just divided by 1 hour, right? But I'm still stuck in meters is the problem. Well, how do I get out of meters? Well, if I multiplied this by 1 kilometer, has 1,000 meters in it, that's only 100, then I'd see the meters would cancel. All right, so let's write this down then. 15 times 3,600 divided by 1,000 hours. Wow. This can kind of deal with this. You're going to see, and this is the conversion that you will always use. I'm just showing you the proof of where it's come from. You can multiply 15 meters per second by 3.6, because 3,600 divided by 1,000 is 3.6. And you will get your answer in kilometers per hour. So it turns out that this answer is 54 kilometers per hour. Does anybody have any questions? I know I made a little hiccup there. Hopefully I didn't lose anybody. But you can kind of see the relationship in what I was trying to do yesterday with like manipulating units, right? And to get to something that I'm actually looking for, right? So you can see here for the velocity in kilometers per hour for car A, we're going to see 54 kilometers per hour. And sometimes it's like, I could tell you it's multiply it by 3.6, but that's not necessarily going to mean anything to you, right? At least if I show you this, right? Then we can kind of have a better understanding as to where that 3.6 came from, right? So if I ever ask you to take something in meters per second and switch it to kilometers per hour, you just take whatever the number is and multiply it by 3.6, right? So for this one, if I multiply by 3.6, I'm going to get 14.4 kilometers per hour, right? And if you guys ever type anything into like Google, like a Google conversion, that's all that's happening here, right? They're just doing the back calculation, all of this very quickly. That's what Google's doing. They've written an algorithm. It's just doing that work, right? It just knows it's 3.6, right? So if I do it again here, times 3.6, we're going to see 28.8 kilometers per hour. And here would be just negative 28.8 kilometers per hour. Does anybody have any questions? Again, like that didn't go. I made one hiccup there, which I made this morning. I told myself I wasn't going to make this morning, but I also put another video up to you. You can watch it, get done again. Okay, if you could watch this video, or you could watch the supplementary one I put into Minds Online. Okay, to help you with that. Does anybody have any questions? Big key question there. If I have a position time graph and I'm asked to figure out what the velocity is, you find the slope, right? You find the change in the distance or displacement and divide it by the time. Okay? So here's what we want to do. So we've got this position versus time graph, right? This is just a motion of an object, and it's plotted its position relative to time. And what this wants us to do is describe exactly what's going on here, right? Okay. So it looks like, okay, well, in the initial stages here, if I look at that graph, it looks like that thing, whatever this is, like a dog or a person riding a bike or something, right? Or walking, right? It looks like relative to the rest of the graph, right? Like you're trying to look at all of this, like the whole thing. You're thinking to yourself, how does this slope compare to this one? Well, this slope here is much steeper, right? So if I found the slope like what we found in the last question, its speed is going to be much higher than right here because it's not as steep, right? The number that I'm going to get when I do the rise over run is going to be much higher. So like qualitatively, I'm going to write, okay, moving fairly quick in the eastward direction. Okay, and then for part B, slows down, but still walking in the east direction, right? Or we could even say part B is walking and part A is running, right? Okay, and then part C, this is where like, this is a key point, a key little phase. What is the slope of part C here? Let me know. Like, if you just think back to your math, what's the slope of line segment C? Arrest. Yeah, Jagger's right. So if you were to do the rise over the run on this, you'd get a slope of 0. Well, we know in context, a slope on a position time graph is velocity. Right? So we know that the velocity is equal to 0, which must mean that they're not moving, right? So it means that they're resting. Okay, and then it looks like steps like part D here. I think that's really, really quick. I think that's steeper than part A. So it'd almost say, okay, they're sprinting, but they're sprinting in a negative direction. Like your slope would be negative. So we're going to be sprinting in the westward direction. Okay, and for part E, we'll say, okay, they took kind of a rest and from sprinting, and now they're walking again. Is that okay? Okay, so what I want you guys to do is if we're just going to calculate the velocity, right? This is the exact same exercise as above, okay, where we're finding the slope. Okay, and just for the interest of time, I'm just going to give you the answers, right? So we're just going to say, okay, it's the exact same. Finding the slope between 2 points. The slope on a position time graph represents the velocity. Remember, when we write velocity, when you see the word velocity relative to the word speed, you have to include which direction that they're going in, eastward or westward, right? Depending if it's positive or negative. Okay, and so for this, if I were to calculate the slope of line segment A, we're going to see that it's 4 east. And for B, we're going to see 1 meter per second east. For C, 0 slope, 0. I wouldn't even put a direction on it. They're just standing still. Right? They can't be moving anywhere. Like, they're not moving in any particular direction if they're not moving at all. Right? So I don't think we need a direction there. D, I'd say, okay, we have negative 7 meters per second. Or you could write 7 meters per second west. And for part E, we could say negative 1.6 meters per second, or 1.6 meters per second west. Okay? Now, there's a couple other things we can read off of here, and we saw some of this yesterday. With this question, we're trying to make the distinction between distance and displacement. And we saw, this is almost like the picture from yesterday's note where there's the bike going around, right? And we saw the difference between the distance and the displacement, right? So it looks like, if I were to look at this, it looks like they're walking or running up. Well, they go 12 meters in the eastward direction, and then they go another 2 meters, and then they stay at rest. So we've traveled a total of 14 meters so far, right? And then they turn around and they go the other 14 meters back down, right? And then they go another 4 meters. So the total distance traveled, ignoring the directions, would be the 14 plus 14, which would be 28, plus another 4, right? So the total distance traveled would be 32 meters. Now for the average speed, we know speed is just velocity with no direction, right? But we're going to take the total distance traveled and divide it by how long it took them to get there. So for this one, we know it's the 32 meters. How long did it take the whole trip? It took 12 seconds. So divided by 12 seconds. 32 divided by 12 should be 2.67 meters per second. You don't need direction because it's just asking for the average speed across the whole thing of motion. And now, for part B, it's explicitly asking for the displacement, right? And so I don't care about the fact that it went all the way up and then turned around. It's asking about the displacement. So from here to there, it's like a vector, right? We saw these yesterday. This would be the delta D vector. You see that okay? Sorry, the green's not too good. I'm asking for the displacement. That's the displacement vector, right? It started here and it ended here. That's the displacement. Okay, well, what was the displacement? Well, it went negative 4 meters, right? Or 4 meters west. Okay, what would be the velocity? The velocity, if you were to draw a vector on here, like what we just did, you could find the slope of that vector, right? And it would tell you what the velocity was, right? It's the exact same thing. Or you could use the equation, right? We know that if I took the displacement of 4 meters and I divided by how long that took, be 12 seconds, you're going to see 0.33 meters per second west. Okay? If you were to calculate the average velocity from 3 to 8.5 seconds, so from here, remember we're talking about velocity, so we're talking about the green vector. We're not talking about the speed, right? If it asked for the speed from I'll use a different color, from 3 to 8, that's much different. This is speed, but it's asking about the velocity from 3 to 8. Well, it's the same answer because the slope is the slope, right? It has to be this answer right here. Okay? Or if you found the slope might be just subtly different between these 2 points, right? It might be 3/6 or something if you found the slope. Okay, but it's very, very close. Okay, and the thing with finding the slope is you could be off on your graph at all, right? And then that's going to create some inconsistencies, but it's going to be close. The last one's kind of a challenging question, okay? Describe using the graph above an example where the average velocity is 0, okay? So average velocity is 0, but the average speed is not 0. Because there's one point in particular that I think stands out to me. Okay, and if you guys always take the mindset of velocity being the displacement divided by the time, there's one spot on this graph where the displacement is 0, right? That occurs. Sorry, what color should I use? How about pink? Where the displacement is 0 is right here. If I drew a vector, a displacement vector, that's equal to 0. There's no change, right? So that'd be an instance where the displacement, if I took the displacement of 0, delta d divided by t, while delta d was, with the arrow, the vector, displacement, was 0 divided by, it doesn't matter, 9 seconds, that's going to be 0 meters per second, right? With a vector on it, or a direction. Okay? But if I look at that very same point, the speed at that point is not 0, right? You can tell that the object is moving through there, right? And so it's at the point 9.5 seconds that the speed and displacement is to create this unique situation where the velocity is 0, but its speed is not. Is everybody okay with that? Okay, I'm just monitoring the chat. Okay, if you guys ever need anything, just throw it in there. Okay. Okay, that's good. That's good. This is not. Sometimes this is not easy, right? Like it takes some review, and even like going back, like after having not done doing it for very long, right? You come back and you're like, okay, I got to make sense of these things again. Like these come and go, but they end up coming up in first year physics where they're like, here's the motion of an object, and you're like, oh yeah, I remember doing this, but I can't remember all the rules, right? I think I've done an okay job at, like, now that I have a math background, like contextualizing this from a math perspective, very sequential, right? And so what I want to do here, just before we go, and this might take a little longer than 11, right? I'll at least do the first one. Okay, what happens, and this is what I was alluding to this morning, from the standpoint of, like, you got to pay very close attention to the axes. Okay, because the type of graph that you're looking at tells different stories, right? And sometimes it's like, oh, so if you're looking at this with a position versus time lens, that's much different than the velocity versus time. Okay, and so what we saw is up top is I gave you a graph in the position versus time, right? Like I gave you something that did something like this, right? Position of an object. And you guys were able to find maybe not something quite like that, but you know, like if I gave you something, like you guys could figure out finding slopes, what the velocity graph would have looked like, right? But this time I didn't do that. I gave you the velocity. So if I'm interested in going from here to here, right, you guys are asking yourself, okay, well, how do I do that, right? Well, above, to go from here to here, we found the slope. But let's take a look at if I was given the velocity and I wanted to go to like distance. So for instance, if you guys have some familiarity with this, if I drew your little triangle, I'm interested in distance this time, or the position of this object, right? Well, if I covered up the distance, how would I get that? Well, I take the velocity or speed and multiply it by the time, right? Well, that means I'm going to multiply this by this, which basically means when I multiply it, if I'm going to find the areas, right? So the area underneath a velocity time graph, and I'll write this down somewhere just as a rule. Okay, so to go this way, you're going to find the area. Okay, and so what's that mean? Okay, well, let's find the area of this pink section. What's that? Well, it looks like I've got 30 high by 1 second long. So I take 30 meters per second and I multiply it by 1 second. Well, the units cancel. What are you left with? 30 meters. That's how much distance was covered in the first portion of this graph, in this pink portion. 30 meters. Okay, well, what's that mean? How do I create that on the graph? Okay, well, let's start by labeling our axes. Okay, so for 1 second, and you'll see when you draw these things, you can see I've drawn these dashed lines, right? Because the time is the time. You're interested in, okay, well, here's the motion of the object for the first 1 second. Here's its velocity graph. Well, the time can't change, right? So you just want to know how far did the object travel in the first 1 second, given this velocity graph, right? We say, okay, well, I found how far it went. So you say, okay, well, it went 30 meters. That came out to be positive, right? So you're going to go, okay, well, that's fine, right? Now, the next portion, a little bit trickier, right? Because now I've got two areas, right? So you got one area here and one area here. Well, if you were to find the area of the triangle there, you know the area of a triangle is 1/2 the base times the height. Well, how's that work out? Well, the height goes from 10 to 30, and the base goes from 1 to 3. So the base is 2 times 20, because that's how high it is. And you got to multiply that by 1/2, right? So the 2's cancel. You're left with 20 for this. But don't forget about the fact that it's the area underneath of the graph that represents the position. So you got to add in this area here. So the second area, you're going to have, we go from 1 second to 3 seconds, so that's 2, but its height is 10. So you're going to go 2 times 10, which is 20. So you're going to add these two together, and for this portion of the graph, the blue portion, the object covered 40 meters, right? And a position, you just got to add it. You got to continually add it, right? And so you're like, okay, well, 30 plus 40, that's going up to 70. Okay, and for the last one, the little section here, the green section, we have 1 second wide multiplied by its speed, 10. I'll write that differently. Seconds canceled, so you're left with 10 meters. So in this last portion, the green portion, you're going to travel another 10 meters. Right? You can see the points on here. You can say, okay, well, this is 130. This is 3 and 70. And this is 4 and 80. Okay, and then you say, okay, what's this look like? What's the position versus time graph look like? Well, you just kind of connect the dots, right? Now, the one thing you have to pay attention to, and this is going to get into this afternoon's lesson, and I'll come back to this after, particularly with this question. I'll lead off with this question this afternoon. But you know, if you have zero slope on a velocity time graph, it means that the velocity is not changing, right? And so it's moving at a constant rate from where it started to where it ended up. Okay, it's a straight line, slope. Same thing happened over here, is I got another straight line, right? And so from there to there is another straight line. The problem is, in between these two things, the velocity in the middle, for the blue portion, it looked like the velocity was changing. Like there was a slope there, right? There's no slope here and no slope here, but there is a slope here. That means one particular thing, and can somebody drop it in the chat? If the velocity is continually changing, what is that? And somebody mentioned it earlier in the chat already. You know, if your velocity is always getting faster and faster and faster and faster and faster, what do we call that? Acceleration. Or what if your velocity is slowing down? We call that deceleration, right? And so our graph has to be depicted like that, right? So our position graph, it looks like the slope here is negative. So that means the velocity of the object is slowing down, slowing down, slowing down, slowing down. So its position relative to time, as time goes on, it's not covering as much distance because it's slowing down. And so our graph in between here has to be kind of curved down very slightly, right? Because it's the amount of distance that it's covering is decreasing with time because it's slowing down. Okay? That sets us up, okay, for this afternoon where we're gonna have an acceleration versus time graph. Okay? You guys will see what that looks like.